Okay, so we just talked about the energy diagrams. Now we're going to go into the second law of thermodynamics. So the first law dealt with enthalpy, the change in the energy and reactions. Now we're going to talk about entropy, okay? Entropy is interesting, okay? As you read, I hope you didn't get too confused. It's just very different than what we've been dealing with. Entropy is the measure of disorder that exists in any system. Okay, so when you hear entropy, you should think craziness, chaos, the amount of disorder. Okay, it's a measure of disorder. So it can come in many different units. Okay, they list them all they list some of them at the top of page 440. We're not going to delve into that quite yet. You need to know that entropy is the abbreviation we give it is the capital S. Okay, just like enthalpy was at H, we found delta H. Now we've got entropy, and it's an S, and we're going to find delta S, okay? So it might seem kind of strange that scientists can measure disorder, but it turns out that it's really fundamental to how you view life. So as we walk through it, you might be like, oh, okay, well that makes more sense than I thought. So they give you, in figure 13.3, they give you an example of a vase with flowers sitting on a mantle. And they say it's in a state of low entropy. Low disorder. Okay, everything's ordered. It's where it should be. It's sitting there. Well, what happens if the vase, by some means, falls to the floor and crashes and breaks? The flowers are everywhere. The pieces are everywhere. We would say that's in a state of high entropy, high disorder. Okay, it went from an ordered state, what it should be, and all of a sudden it's a mess. It's broken. There's pieces. Okay, so it went from a low state to a high state. That happens in real life, right? You knock things over, they break. Is there any, do you find that often you'll have a broken vase on the floor, or a broken, let's say, a glass of water you had sitting on the counter? Is there ever a shattered glass on the ground that all of a sudden, while you're standing there, it goes and all those pieces come back up and form itself into a glass of water on the counter? No, we don't find that in our world. Okay, in our universe, it never goes backwards. Okay, so that should make sense to you. That sounds crazy. It's because that's not how it works. So the whole idea of entropy is things always go from an ordered state to a disordered state, or they stay the same. Okay, so your entropy, your measure of disorder, it either has to get more disordered or stay the same. It never can decrease. Okay, so that is the second law of thermodynamics. It states that the entropy of the whole universe must always either increase, get more disordered, the whole universe is getting more disordered, or it must remain the same. It can never decrease. So really what you're saying, the order of the entire universe as a whole never gets less disordered. Okay, so you can kind of see how that's important, because to an extent, that determines what types of events are possible in nature. Some events are not possible. If it gets more ordered, it's not possible. So we're going to talk a little bit more about that in detail in just a second. But first, we need to talk about ways that things can become more or disordered. Okay, and so that's what this is of. Okay, so as we go up this in each one of these categories, entropy or disorder is going to increase. Okay, and this will make sense as we talk through it. So if I have a solid, liquid, and a gas, as I go from a solid up to a gas, disorder increases. And this should make sense, okay? Because in a solid state, it has the least amount of entropy or disorder, okay? The molecules are really close together, they're vibrating, they can't get anywhere, okay? As we go to a liquid, they're able to move about more, right? And as a gas, they're bouncing around everywhere because there's more energy the more that we go from a solid to a liquid to a gas. Well, it kind of makes sense, right? If you think about like a toddler sitting on the ground, if he's strapped into, let's say he's strapped into his car seat, he can't really move very far. He's kind of like a solid, right? He can't really cause much disorder besides what he or she can reach. But if they're let's say you have them kind of in just one room full of toys, they can cause a certain amount of disorder, but only a certain amount, right? They're more disordered than they were in the car seat. Well, what if you let them have free range of lots of things that they shouldn't get at, right? That's even more disorder. That's kind of like a gas would be, okay? So the more energy you're adding as the molecules move around, the more disordered it gets, okay? So that has to do with phases. Now think about it from a temperature point of view. Obviously a solid is a lower temp. Things are solid at a lower temp. The higher the temp goes, the higher the energy gets, so the temp goes up. So in the same way, entropy increases, okay? So if you have heat to something, you're automatically adding more disorder because of that increase in energy, okay? And last, less matter versus more matter. This should make sense. I think the book gives a great example of this, of your bedroom, okay? You can, if you have less stuff, let's say you only have one suitcase full of things for your whole room, you're gonna have a spot for everything, right? You can only have so much mess or so much disorder in your room. Well, what if you have a bunch of stuff? You got, your TV, your PlayStation, all these different things going on in your room. You have a high level of a chance for disorder. The more things you have, the more disordered things can be, okay? So we're gonna keep these things in mind as we talk about entropy or disorder, okay? So in general, the universe as a whole has to get more disordered. So we would say in a common term, I'm gonna write it in between here, the change in entropy or the change in disorder, it must always increase or at least be equal to 0. It can never go negative. You can't go backwards. It can't be more ordered. That's what this means, okay? So real quick, before we dive further into what that means, let's just look at these first couple examples, okay? I have A, B, and then C. I didn't write out, it's really long, we'll get there in a second. So it says, for each reaction, determine the sign of delta S, which is just change in entropy, change in disorder, okay? So what we're gonna determine based off of this, what we're talking about, in terms of our reactions, this is how it applies. When we look at these phases, solid, liquid, gas, we should be able to tell, this is why these phase symbols are so important. We should look solid, aqueous, aqueous, gas. This is basically a liquid, okay? The most disordered, the highest state of entropy is gonna be your gas, followed by your aqueous and liquid, followed by your solid. So basically, we're just gonna compare both sides, okay? We're gonna compare this side and see which one has a gas. We'll always start with the gas, that's the most disordered. So if I look between these two, this is the only side that has a gas. So this is how I'm gonna notate this. The book doesn't really show you, but this is how I do it. I look to see which one's the most disordered, gases. And now we compare the gases. Are there any over here? No, 0. How many are over here? I look at my coefficient, there's only 1. And now I say, it went from 0 to 1. And if I think of a number line, okay, here's my number line, here's 0, here's -5, and a +5, okay? If it goes from a 0 to a 1, that's a positive, you're moving towards the positive side, right? So I would say that this is positive change of entropy, okay? Let's look at the next one. We're just gonna be comparing each side. Gas, gas, gas. So now we can compare all of these, okay? So we're gonna add up our gases. We have the number 1 sitting here, 1 and 3. So total, I've got 4 gases here. Over here, I've got a gas, and I only have 2 of them. So I'm gonna compare 4 to 2. Going from a 4 to a 2, I'm heading negative, right? So I would say this is a negative change of entropy, okay? So that's what they're asking. They're asking what the sign is. Is it positive or negative? The last one. This one's really long. I didn't bother to write out all of these. Really, the only thing we're looking at are our phase signs, right? So I've got solid, solid, aqueous, aqueous, liquid, okay? So if we look at this one doesn't have any, it's just a solid. These have at least a liquid or aqueous. They're the same. So just by default, this has none of the liquid or the aqueous. And we could look at that. You could count them, 1, 2, 8. We already know that this side is higher, okay? So we could make a play saying 10 or something like that. Or if we just wanted to go with liquid, we could even just say 8 if we were comparing liquids, okay? Either way, we see that this is moving on our number line from a 0 and it's going positive. So I would say this has a positive delta S, a positive change of entropy, of disorder. Okay, so you're going to do that on your own 13.9, A, B, and C, and you're going to be looking at your phases. Okay, this is why this matters, these phases here. As you go up, solid, liquid, gas, it increases in entropy. So always start with gas. If you've got gas, one gas, you just go ahead and list it like we did here. There were no gases here, so we put 0. There was one here, and that tells you whether it's positive or negative. So go ahead and practice that really quick. Okay, so hopefully that was pretty easy. So we're just starting with entropy there. That's deciding whether it's positive or negative. Okay, now we're going to talk about what that really means. Okay, so we've already talked about delta H, okay, right here. We've talked about bond energies and Hess. That's the change in energy. Now we're talking about the change in entropy, okay? Thankfully, the change of entropy is, we can use Hess's law for it, okay? It's got the same, all substances, the only difference though, so this little, I think the book talks about it, this means summation, okay? You should have already learned this in algebra. That just means the sum of, okay? So the sum of the products minus the sum of the reactants, this is the same thing that's stated here, okay? So we can use exactly what we were doing, finding delta H with delta S, okay? The only difference that you have to be aware of is that when you're dealing with entropy, that all substances, even elements like O2, N2, all those things, they have absolute entropy. So that means that when we use this equation, elements do not equal 0. So in this case, they're either going to give you the element number or they're going to have you solve for it, okay? So go ahead and take a look at the next table. So now we're introducing another table. We had bond energies. We just used the delta H table for Hess's law. Now we're on table 13.3. This is from the appendix. And you can see I put a little delta H, delta S, okay? So this is where I go to find this. And then I put little notes. Elements equal 0 for this. Elements do not equal 0 for this, okay? So this table's in your book right here too. And then they're going to say, okay, go ahead and do that on your own. So for 13.10, you're literally going to do exactly the same thing. They give you an equation, and they say, okay, now calculate the change in entropy, the change in disorder. You're going to do exactly the same thing. Take your product side, and you subtract your reactants. It's exactly the same, okay? The only difference is if you come across an element, which in this one you don't, there's no just raw elements, then you would have to have a number for that, okay? We'll get to that in our practice problems. This one's fine. Go ahead and do it, and then we're going to keep going. Okay, now I want to talk a little bit more about this second law of thermodynamics. What I said was not fully true, because if you think about it, the fact that everything has to go from an ordered state to a more disordered state. It can't go more ordered, okay? Well, then the book makes a very good point. And you might be thinking, okay, well, the whole idea of evolution is that things started out just basic, smudge, basic things. And somehow it randomly evolved into something. So what was disordered pieces all of a sudden became ordered pieces, okay? How is that not going against the second law of thermodynamics? Well, what I said before, it sounds like it, but remember, the key word here is the universe, the total, okay? So we might be looking at one little thing going from nothing pieces into an animal, okay? But what you're not thinking about might be the things around you, okay? So think about it this way. I think the book is this description. If you are cleaning your room, let's say your room's really messy, okay? And your mom tells you to go clean it. You go upstairs and you clean your room. So your room goes from a disordered state to an ordered state, which seems to be totally against the second law of thermodynamics, okay? That shouldn't be. And don't try to use this to tell your parents